Space is not the stage of reality, but a grand illusion. Beneath the smooth fabric of our universe lies a hidden scaffold of pure connection, a theory so radical it rewrites our cosmic origins. This is the EREPR proposal, a mind-bending idea that says space-time and gravity are not fundamental. They are emergent phenomena, a cosmic mirage conjured from a vast, seething network of quantum links. By the end of this journey, you will understand how our entire three-dimensional world could be a hologram projected from a web of entangled information. We will uncover how wormholes might be hiding inside every particle and ask what existed before the Big Bang if space itself had not yet formed. What does it mean for our reality if the distance between stars is just a story told by quantum threads? This proposal has a name, one that sounds like a secret code for the universe itself, EREPR. It stands for entanglement, reconstruction, and the emergence of spacetime. At its heart is a single, staggering claim: the three-dimensional space we move through, the gravity that holds planets in orbit, even the relentless forward march of time, these are not the bedrock of reality. They are a magnificent side effect. They emerge like the wetness of water or the temperature of a gas from something far more fundamental. That something is a vast, churning ocean of quantum information. Think of it as the ultimate cosmic blueprint, a network of countless interconnected quantum bits or links. Each link is a simple yes or no, a 1 or a 0, but their connections are everything. This is where the magic happens. The geometry of space, the very distance between 2 points, is not a pre-existing stage. It is a story written by the pattern of entanglement, the quantum threads that stitch these information bits together. The more entangled 2 bits are, the closer they are in the emergent space that we perceive. This flips all of classical physics on its head. Newton saw gravity as a force acting across empty space. Einstein refined it, describing gravity as the curvature of spacetime itself. But in the EREPR view, even that curved spacetime is a secondary character. It is the holographic projection, the three-dimensional movie, playing out on a two-dimensional screen of quantum links. The screen is the real reality, and everything we see and feel is its breathtakingly complex output. For nearly a century, physics has been caught in a silent civil war. On one side stands the majestic theory of general relativity, Einstein's masterpiece. It describes the cosmos with breathtaking elegance, painting gravity not as a force but as the graceful curvature of spacetime itself. It tells us how planets dance, how black holes form, and how the universe expands. Its domain is the vast and the heavy, the realm of stars and galaxies. On the other side stands the bizarre and brilliant framework of quantum mechanics. This is the rulebook for the subatomic world, a place where particles can be in 2 places at once, where information seems to teleport through entanglement, and where reality remains fuzzy until observed. Its domain is the tiny and the light, the realm of atoms and photons. Both theories are spectacularly successful in their own territories, yet when they are forced to meet, the result is not a unified understanding, but a screaming mathematical contradiction. This is the great unsolved problem of quantum gravity. General relativity describes spacetime as a smooth, continuous fabric, like a tranquil sheet of rubber. But quantum mechanics tells us that at the very smallest scales, this fabric should be a frenzied, foaming sea of virtual particles popping in and out of existence. The equations of gravity simply break down when applied to these quantum fluctuations. It is as if one law governs the ocean's tides, while another, utterly incompatible law governs the individual water molecules. We know both are true, but we have no single language to describe them together. This century-old impasse is more than a technical puzzle. It is a fundamental crack in our understanding of reality. It means we cannot describe the fiery singularity at the heart of a black hole, or the first searing moments of the Big Bang itself, our two most powerful descriptions of the universe are at war. This profound crisis is precisely why ideas like the EREPR proposal are not just interesting, they are necessary. When the old maps fail, you must be willing to consider that the territory itself is stranger than you ever dreamed. These quantum links are the silent architects of our perceived reality. To understand them, we must first let go of our most basic intuition. Do not picture them as tiny threads or physical wires. They are not objects you could ever see or touch, even with the most powerful microscope. Instead, think of a quantum link as a pure relationship, a fundamental bond of information shared between the simplest possible units of reality, which we call quantum bits or qubits. A single qubit is a universe of possibility in itself. Unlike a regular computer bit, which can only be a 1 or a 0, a qubit can exist in a state called superposition. This means it can be both 1 and 0 at the same time, a simultaneous yes and no, a spinning coin that is somehow both heads and tails until you look at it. This strangeness is just the beginning. When two or more qubits become entangled, their individual identities dissolve into a shared state. Their fates are woven together, no matter how far apart they may later seem to be in our familiar space. Change the state of one entangled qubit, and its partner responds instantly, as if they are two ends of a single, invisible connection. This is the quantum link, a bond that defies our classical notion of separation. Now scale this idea up to an almost unimaginable degree. Picture not 2 or 3, but countless trillions upon trillions of qubits, all humming with potential, all entangled in a vast, ever-shifting web of these relationships. In this seething network, there is no up or down, no here or there, no distance at all. There is only connection. The strength, the number, and the pattern of these quantum links define everything. In this fundamental view, what we call space, the three-dimensional arena where events unfold, does not exist. It is an emergent property, a story that only makes sense when you step back from the microscopic tangle. Think of it like the experience of watching a movie on a high-definition screen. If you press your nose against the glass, all you see are individual, glowing pixels, red, green, and blue dots. They have no inherent image, no landscape, no characters, but as you move back, those pixels organize in your perception. The relationships between their colors and positions create the illusion of depth, of movement, of a whole world. The quantum link network is that screen of pure pixels. Our smooth, continuous spacetime is the immersive movie our brains, or rather, the laws of physics, assemble from that raw data. The distance between two stars, then, is not a pre-measured gap in an empty void. It is a direct reflection of how many quantum links, how much shared entanglement, exists between the information that represents those stars in the underlying network. Less connection means a greater emergent distance. More connection means they are closer. In this way, geometry itself is born from relationship. So the next time you look up at the night sky, consider a profound shift in perspective. You are not looking out across a vast emptiness. You are witnessing the breathtakingly complex output of a hidden tapestry, a cosmic fabric woven entirely from threads of quantum information. This emergence is the universe's greatest magic trick, where something entirely new and unexpected appears from a crowd of simpler parts. We see it everywhere in nature, yet its implications for reality are staggering. Take the concept of temperature. If you could shrink down to the scale of a single air molecule, you would find a chaotic world of frantic motion. Each molecule zips and bounces, possessing only its own individual speed and direction. At this level, the idea of temperature is meaningless. You cannot point to one molecule and say it is hot, but step back. Look at the collective dance of trillions upon trillions of these molecules. From that unimaginable complexity, a new, stable property emerges: temperature, a single number that describes the average kinetic energy of the whole. It is a property of the crowd, not of any individual member. The wetness of water is another beautiful example. A single water molecule is not wet. Wetness is a property that only manifests when a vast collection of these molecules interact in just the right way, creating surface tension and adhesion. The whole becomes something the parts could never be alone. This is the essence of emergence, and it is the precise key that unlocks the EREPR proposal's vision of spacetime. Our underlying quantum network is that sea of frantic molecules. Each quantum link, each entangled qubit, is like a single pixel on a colossal screen. A pixel by itself holds no image. It is just a point of colored light, but arrange billions of them in a specific, interconnected pattern, and from a distance a coherent picture emerges. You see faces, landscapes, entire worlds. Your brain does not perceive the individual pixels, it perceives the smooth, continuous image they create together. Now apply this to the fabric of the cosmos. The quantum link network is that pixel grid operating in a realm with no inherent space or time. The individual links are discrete, yes or no connections. There is no smoothness here, only a vast digital tapestry of pure information. But when we, as complex observers within the system, interact with this network at a grand scale, something miraculous happens. The collective pattern of entanglement, the density and strength of those countless quantum threads, gives rise to a smooth, continuous geometry. The distance between 2 points in this emergent space is not measured with a ruler. It is calculated by the amount of quantum entanglement or shared information between those regions of the network. Areas with a dense web of connecting links appear close together. Regions that are only weakly entangled appear vastly far apart. In this way, the three-dimensional expanse of the universe with its mountains, stars, and galaxies is the emergent image. The underlying, churning quantum connections are the pixels. We are not living in the network, we are living in the picture it paints. This solves a profound puzzle hinted at by the war between gravity and quantum mechanics. General relativity demands smooth, continuous spacetime. Quantum theory suggests a fundamental graininess at the smallest scales. Emergence beautifully reconciles this. Yes, the fundamental level is discrete and grainy, a digital reality of information bits. But just as a digital photograph can appear perfectly smooth and continuous when viewed from a normal distance, so too does our spacetime emerge as a smooth, classical reality from the quantum grain. The wrinkles and curves in this emergent fabric, what Einstein described as gravity, are then simply reflections of how the entanglement pattern within the hidden network is woven. A massive object like a star is not bending a pre-existing stage. It is a region where the quantum links are configured in such an intensely connected way that the emergent geometry curves around it. We are left with a breathtaking inversion of reality. Space is not the container for things, it is the story told by the connections between things. If quantum links are the threads, then entanglement is the force that weaves them into a fabric. This is the revolutionary leap at the heart of the EREPR vision. For decades, quantum entanglement was seen as a bizarre but useful quirk, a tool for quantum computers and secure communication. Yet here it is promoted to the most fundamental role imaginable. It becomes the quantum glue, the very substance from which the geometry of reality is constructed. Think of the underlying network not as a static grid, but as a dynamic, living tapestry. Each connection between qubits is not just a line, it is a bond of shared knowledge, a correlation so deep that the states of the two qubits are forever linked. Now the critical insight is this: the strength and density of this entanglement fabric directly dictates the shape of the space we experience. Picture two distinct regions within this vast quantum network. In our emergent reality, these regions might correspond to two distant stars. How far apart are those stars? The classical answer would involve measuring the empty space between them. But the EREPR proposal offers a far more profound answer. The distance is not a primary feature of empty space because at this fundamental level there is no space. Instead, the distance emerges from the informational relationship between the regions. If the qubits in region A and the qubits in region B are richly and densely entangled with one another, sharing a vast amount of quantum information, then in the emergent spacetime, these two regions will appear very close together. They are intimately connected in the hidden reality, so their projected images are neighbors. Conversely, if the entanglement between region A and region B is weak or sparse, if they share very little quantum information, then in our perceived universe they will appear to be separated by a vast cosmic gulf. The geometry of space, the very concept of near and far, becomes a direct readout of quantum connection. This bridges two seemingly alien worlds, information theory and gravity. Information, measured in bits and entanglement entropy, is no longer an abstract concept used by computers. It becomes the raw material of physical reality. The curvature of spacetime, which Einstein showed is the manifestation of gravity, then receives a stunning new interpretation. A massive object like a planet is not merely sitting in space and bending it. Instead, the planet corresponds to a specific, intensely knotted configuration of entanglement within the quantum network. This dense knot of information warps the local pattern of connections, which in turn warps the emergent geometry around it, creating what we perceive as a gravitational well. Gravity, in this view, is not a fundamental force pulling objects together. It is a thermodynamic force, an entropic tendency that arises from the universe's natural drive to maximize the entanglement within its quantum network. It is as if spacetime itself is elastic because the quantum connections prefer to be in a certain state of complexity. This idea turns our intuition about the cosmos inside out. We are not living in a container that then contains entangled particles. We are living inside the emergent consequence of those particles, or rather, those fundamental information bits being entangled. The void between galaxies is not an empty stage, it is a story of minimal connection. The fabric of spacetime is not woven from a mysterious ether. It is woven from the silent, invisible threads of quantum information shared across the universe. The name itself holds the key to this cosmic unification. EREPR is not a random string of letters, but a profound equation written in shorthand, a declaration that two of the greatest puzzles in physics are in fact two sides of the same coin. To crack this code, we must meet the ghosts in the machine, the legendary figures who first outlined these deep mysteries. The second half, EPR, stands for Einstein, Podolsky, and Rosen. In 1935, these three physicists published a paper that was meant to be a critique, a way to show that quantum mechanics must be incomplete because its predictions were, in their view, absurd. They described a thought experiment now known as the EPR paradox. Imagine two particles created together, like twins born from the same quantum event. According to the theory, these particles become entangled, their properties forever linked. You could separate them by any distance, send one to the far side of the galaxy. Then, by measuring a property of the particle in your lab, say its spin, you would instantly know the spin of its twin billions of light years away. This spooky action at a distance, as Einstein famously called it, seemed to violate the cosmic speed limit set by his own theory of relativity. How could information travel faster than light? For Einstein, this was proof that quantum theory was missing something, some hidden variables that predetermine the particle's states. He believed there must be a local reality where objects are only influenced by their immediate surroundings. The EPR paradox became the defining challenge for quantum weirdness, a ghost that has haunted physics for generations. Now, let us look at the first half of the name, ER. This stands for Einstein and Rosen. In the very same year, 1935, Einstein collaborated with Nathan Rosen on another groundbreaking paper. This one tackled gravity and the structure of spacetime from the perspective of general relativity. They mathematically explored the possibility of bridges connecting distant regions of the universe, tunnels through the fabric of reality itself. We know these structures today as wormholes or Einstein-Rosen bridges. In their equations, these were not traversable tunnels for science fiction heroes, but more like cosmic shortcuts, geometric structures where two black holes could be connected at their singularities. For decades, these two ideas, EPR entanglement and ER wormholes, lived in separate worlds. One was a quantum mystery about instantaneous connection. The other was a gravitational prediction about geometric shortcuts. They came from the same mind, yet they seem to describe entirely different layers of reality. This is where the modern revolution begins. The equals sign in ER equals EPR is one of the most daring conjectures in theoretical physics. It proposes that these are not two different phenomena. They are the same thing, described in two different languages. The conjecture states that every instance of quantum entanglement, every spooky EPR pair, is physically manifested in the emergent geometry as a microscopic wormhole, an Einstein-Rosen bridge. When two particles are entangled, they are not communicating faster than light across a void. There is no across at the fundamental level. Instead, their quantum link is the geometric equivalent of a tiny, Planck-scale tunnel stitching their locations together in the emergent spacetime. The entanglement is the wormhole. This single equation performs a miraculous act of translation. It takes the language of quantum information, the yes or no states of qubits and their spooky correlations, and translates it directly into the language of geometry, the curves and tunnels of spacetime. It says that the fabric of reality is literally woven from these quantum threads, and where the threads are strongest, they pull the emergent geometry into a connective structure. This bridges the century-old war in a breathtakingly elegant way. The non-local weirdness of quantum mechanics finds a home in the local geometry of general relativity. The wormhole is not a tunnel through space. It is what constitutes the connection we perceive as space between those 2 points. The greater the entanglement, the more robust and shorter the wormhole, making the 2 points effectively closer in the emergent world. Suddenly, the universe is not filled with particles and empty space. It is a vast dynamic network of quantum links, each one a potential stitch in the cosmic fabric, each entanglement a hidden tunnel in the geometry of everything. But how can a higher dimensional world emerge from a lower dimensional one? This is not just a philosophical question, it is a mathematical reality known as the holographic principle, and its most precise formulation is a discovery that reshaped physics, the anti-de Sitter/conformal field theory correspondence, or a DS/CFT. To grasp its power, picture a can of soup. All the rich, three-dimensional stew inside, with its chunks of vegetables and meat, contains no more information than the two-dimensional label wrapped around the outside. Every ingredient, every flavor, every possible description of the soup's interior is somehow encoded, pixel by pixel, on that flat label. This is the essence of holography. In a true hologram, like the kind on a credit card, a three-dimensional image is reconstructed from a flat, two-dimensional surface of microscopic interference patterns. A DS/CFT proposes that our universe might operate on a similar, but far more profound, principle. It states that a theory of gravity operating in a certain kind of hypothetical spacetime, called anti-de Sitter space, is completely equivalent to a quantum field theory, a theory without gravity at all, living on its lower dimensional boundary. In this dizzying equivalence, the wild, churning quantum interactions of particles on the flat boundary screen perfectly and exactly describe the warped geometry, including black holes and gravitational waves in the entire bulk volume. It is a perfect dictionary translating between the languages of quantum mechanics and gravity. The EREPR proposal takes this breathtaking blueprint and asks a daring question. What if this holographic emergence is not just a mathematical curiosity for a special kind of universe, but the fundamental operating system for our own? In this view, the vast network of quantum links we have been exploring is the boundary theory. It is the lower-dimensional, non-gravitational quantum system, the equivalent of that two-dimensional soup can label or the flat holographic film. This network exists in a realm without any inherent space or time. Yet, from the complex patterns of entanglement within it, the entire rich, three-dimensional tapestry of our spacetime and the gravity within it emerges, just as the three-dimensional holographic image emerges from the flat film. The quantum links are not in space, they are the code that creates space. This makes the EREPR vision an attempt to build a tangible, mechanical model for how holography actually works. It seeks to show, step by quantum step, how the threads of information on the boundary weave themselves into the fabric of the volume. So when we talk about the universe being built from quantum links, we are not speaking metaphorically. We are describing a cosmic hologram of unimaginable complexity, where every star, every planet, and every one of us is a three-dimensional projection of quantum data written on the two-dimensional surface of reality's deepest layer. This radical vision of a network-built reality has a close and powerful cousin in theoretical physics, a framework that has been working for decades to quantize space itself. Loop quantum gravity takes the smooth fabric of Einstein's spacetime and asks what it is made of when you look at the very smallest scale. Its startling answer is that space is not continuous. It is granular, composed of indivisible units, much like a digital photograph is made of pixels. You cannot divide a volume of space infinitely. There is a smallest possible volume, a smallest possible area. This is the quantum of space, a fundamental graininess at the scale of the Planck length, a distance so minuscule it is 1,000,000 billion times smaller than a proton. But how do you mathematically describe this pixelated geometry? Loop quantum gravity uses elegant structures called spin networks. Picture a vast, ever-changing cosmic spiderweb. The threads of this web are the edges of the graph, and where they meet are the nodes. Each thread carries a label, a number that represents a quantum of area. Each node represents a tiny chunk of volume. The entire intricate web, with its specific pattern of connections and labels, defines the geometry of space at a given instant. It is a snapshot of the quantum structure of the universe. This is not a metaphor, it is a rigorous mathematical description of how space could be built from discrete pieces. Now look at this spin network and then look back at the EREPR proposal's web of quantum links. The resemblance is profound. They are two different languages describing what might be the same underlying reality. In loop quantum gravity, the spin network's edges define quanta of area. In the EREPR view, the quantum links define relationships of entanglement. What if these are two sides of the same coin? What if the strength of a quantum link, the amount of entanglement between two information bits, actually determines the area of the surface that separates them in the emergent space? This would mean that the spin network is not just a static graph of geometry, it is a living map of quantum information flow. The nodes are not just volumes, they are hubs where entanglement is processed and redistributed. The edges are not just lines with numbers, they are the channels of maximum quantum connection. In this fusion of ideas, loop quantum gravity provides the rigorous geometric skeleton, the atoms of space. The EREPR proposal then breathes life into that skeleton by filling it with the dynamic, informational substance of quantum entanglement. It suggests that the reason space is quantized, the reason there is a smallest possible area, is because there is a most fundamental unit of entanglement, a single, indivisible quantum link. You cannot have half an entanglement, just as you cannot have half a quantum of area. This connection offers a stunning possibility. The bizarre, non-local spookiness of quantum entanglement, which seems to defy our notions of space, may be the very reason that space has a discrete, granular structure in the first place. The quantum links are not in space, they are what space is made of. And if that is true, then every twist and knot in this cosmic network holds the secret to gravity itself. Yet for all its breathtaking elegance, the EREPR proposal stands on a frontier, not a finished foundation. It is a map sketched in brilliant intuition, but the territory itself remains shrouded in mathematical mist. The central challenge is stark. While the ideas are compelling and the connections profound, we lack a complete, rigorous theory that can be written down in a single, unified set of equations. Think of it as having the architectural blueprint for a revolutionary new kind of building, one that explains why all the old structures creak and groan, but we are still searching for the exact materials and construction codes to actually build it. Much of the proposal's most compelling evidence comes from a very specific and somewhat idealized mathematical playground, the anti-de Sitter space of the holographic correspondence. This is a universe with a negative curvature, a kind of cosmic saddle shape, and it comes with a convenient boundary where the quantum theory neatly lies. Our real universe, however, is not shaped like that. Observations tell us the cosmos is nearly flat, and more importantly, it is expanding at an accelerating rate, a property of so-called de Sitter space. Translating the beautiful ER=EPR dictionary from the neat, bounded world of anti-de Sitter space to the open, accelerating expanse of our own reality is a monumental hurdle. It is like having a perfect translation guide for poetry written in one very structured language, and then trying to use it to translate free-form jazz lyrics from a completely different tongue. The core melodies might be similar, but the rules are not the same. This leads to the most pressing question for any scientific idea: where is the test? A theory that remains forever in the realm of beautiful mathematics is a philosophy, not a physics. For the EREPR proposal to graduate from a stunning conjecture to a description of reality, it must make predictions that can be checked against our universe. It needs to tell us something we can look for, something that Einstein's gravity or standard quantum theory does not predict. Perhaps it is a subtle signature in the cosmic microwave background, the afterglow of the Big Bang, a faint imprint left from when spacetime itself was first knitting together from the quantum links. Maybe it is a strange statistical pattern in the way galaxies are distributed, a cosmic fingerprint of the underlying network. Or it could be a prediction about the behavior of spacetime at energies so high we cannot yet reach them, in the hearts of black holes or the first instance of the cosmos. For now, these are dreams, not data. The path from conceptual framework to testable hypothesis is long and treacherous. Then there is the simple, stubborn fact of our everyday experience. The world around us feels local and smooth. When you throw a ball, its motion is influenced by the air in this room and the gravity of the Earth beneath you, not by some quantum link with a particle on the other side of the galaxy. Our reality obeys clear, local rules, where causes are connected to effects through points that are close together in space and time. How does this robust locality emerge from a fundamental reality that is built on non-local entanglement, on connections that defy any concept of distance? The proposal suggests that locality is an emergent illusion, much like the smooth image on a screen. But explaining exactly how that illusion becomes so perfect, so absolute in our macroscopic world, is an active and difficult puzzle. It requires showing how the frenzied, interconnected quantum network, when viewed at our scale, settles down into the calm, classical, and local reality we navigate every single day. This is the grand work ahead, to move from a vision of breathtaking possibility to a theory of concrete, mathematical, and observational truth. The journey is far from over, but the destination promises to rewrite not just our understanding of space, but the very meaning of reality itself. The greatest challenge for any theory this profound is finding its voice in the real world. How do you test a claim about the fabric of reality itself when that fabric is the very stage upon which all our experiments are built? The quest for evidence pushes physics to its most creative and daring extremes. searching for whispers of the quantum network in the data of our classical universe. One promising, if incredibly difficult, avenue is to look for the graininess of spacetime. If space emerges from discrete quantum links, then at the tiniest imaginable scales, the smooth continuum should break down into a kind of quantum foam, a seething, chaotic froth. This isn't a metaphor, it's a prediction with potential consequences. One idea is that this foam could subtly blur the images of the most distant cosmic objects. As light from quasars billions of light-years away travels across the universe, its journey through this hypothetical froth might cause tiny, random deflections, a faint twinkling not caused by interstellar gas but by the texture of space itself. Another possibility lies in ultra-precise measurements of distance. If you try to measure a length with a precision approaching the Planck scale, the fundamental grain of reality, the quantum foam should make the measurement inherently fuzzy, as if the ruler itself is vibrating. While we are fantastically far from being able to measure at that scale with current technology, some physicists speculate that future gravitational wave observatories, listening for the faintest ripples in spacetime, might one day detect a background hiss from the foam of the universe's deepest structure. A different approach looks not forward but backward to the very first light. The cosmic microwave background radiation is a snapshot of the infant universe, frozen in time when it was just 380,000 years old. If the EREPR proposal is correct, and spacetime was crystallizing from a dense network of quantum links in those first moments, the process might have left a unique statistical imprint on this ancient light. It would be a cosmic fingerprint, a pattern of hot and cold spots that deviates in a specific, predictable way from the patterns expected by standard inflationary cosmology. Sifting through the exquisitely detailed maps from satellites like Planck for such an anomaly is like searching for a single sentence, written in a forgotten language within the entire text of every book ever written. The signal, if it exists, is buried deep. Perhaps the most ingenious near-term path doesn't look to the cosmos at all, but to a lab bench. This is the realm of quantum simulators. Instead of trying to probe the universe's quantum gravity directly, we can build analog systems that obey similar mathematical rules. Imagine constructing an artificial lattice of supercooled atoms or superconducting circuits where their quantum entanglement can be precisely controlled. By tuning the interactions between these artificial quantum links, physicists could create a miniature, toy model of an emergent spacetime. They could watch how geometric properties like distance and curvature arise from the entanglement pattern they engineer. Does a dense web of connections make 2 points in the simulator behave as if they are close? Does reducing entanglement make them effectively drift apart? While this wouldn't prove our universe works this way, it would demonstrate the mechanical plausibility of the entire concept, showing that the magic of emergence can indeed weave space from connection. These experimental dreams, from cosmic whispers to tabletop universes, highlight a beautiful truth. To test the untestable, we must be willing to listen in new ways, to build new kinds of eyes, and to recognize that the answers we seek may be encoded in the hum of a distant quasar, the whisper of the Big Bang's afterglow, or the synchronized dance of atoms in a vault of liquid helium. The evidence, when it comes, will likely be a puzzle piece we didn't know we were missing, fitting perfectly into a picture of reality we are only beginning to trace. Black holes are not just cosmic vacuums, they are the ultimate crucible for any theory of reality. Their immense gravity warps spacetime to its breaking point, creating a one-way boundary called the event horizon and a central point of infinite density, the singularity. Here are two great theories, general relativity and quantum mechanics, clash in spectacular fashion, producing a paradox that has simmered for 50 years. The black hole information paradox asks a seemingly simple question with devastating implications. When an object falls into a black hole, is all the information about that object, the quantum states of every atom and particle, lost forever when the black hole eventually evaporates? Quantum mechanics says no, information must be conserved. It can be scrambled but never erased. General relativity, in its pure form, says yes, it is irretrievably swallowed by the singularity. This is more than a technical dispute. It suggests our fundamental understanding of physics is catastrophically wrong. The EREPR proposal strides directly into this storm. Its vision of spacetime as an emergent tapestry of quantum links offers a radical and elegant escape route. In this framework, the event horizon is not a stark, two-dimensional sheet. It is a dynamic, seething surface where the quantum link network is woven into an incredibly dense and complex pattern. When matter falls in, its information does not plunge through a geometric boundary and vanish. Instead, it is imprinted onto this network, transforming into a new configuration of entanglement among the quantum links at the horizon. The information is not lost, it is translated. It becomes part of the very fabric from which the black hole's geometry emerges. Think of it like submerging an intricate ice sculpture into a turbulent, hot spring. The sculpture melts, its specific shape disappears, but the information about that shape, the arrangement of every water molecule, is not destroyed. It is transferred into the microscopic motions and interactions of the spring's water molecules, becoming part of the system's total energy and configuration. To an outside observer who only sees the bubbling water, the sculpture is gone, but its essence remains encoded in the chaos. In the EREPR view, the black hole's horizon is that churning spring, and the infalling information is meticulously recorded in the dance of its quantum links. This leads to an even more profound implication tied to the ER=EPR conjecture. Recall that entanglement is proposed to be a microscopic wormhole. The quantum links connecting particles just outside the horizon with their entangled partners, whether inside or elsewhere, are these Planck-scale tunnels. This means the interior of the black hole is not some disconnected void. It is geometrically stitched to the exterior through a vast web of these quantum wormholes, a tapestry of connectivity. An observer falling in would not encounter empty space, but a geometry built from this dense network. This directly confronts another fierce debate, the firewall paradox. This argument suggests that to preserve information, the event horizon must be a searing wall of high-energy particles, a dramatic and violent departure from Einstein's smooth spacetime. The emergent spacetime picture offers a calmer, more consistent resolution. There is no need for a fiery wall because there is no sharp, classical boundary where physics breaks. The transition from outside to inside is a gradual change in the configuration of the quantum network. The horizon is where the pattern of entanglement becomes so complex and scrambled that it effectively encodes the interior geometry. An infalling observer would not hit a discontinuity, but would simply pass through a region where the local emergent geometry is being generated by an increasingly intricate weave of quantum links. The paradox dissolves because the sharp division between in and out was always an illusion of the classical picture. In the true quantum gravitational description, everything is connected. The black hole, therefore, is not a destroyer of information. It is the universe's most extreme data processor, taking ordered information and transforming it into a spectacularly complex pattern of quantum entanglement on its surface, a pattern that then dictates the very curvature of spacetime around it. The information is never gone. It is woven into the deepest structure of reality, waiting in the links. If black holes are cosmic data processors, then the Big Bang must be the ultimate origin story for information itself. The standard cosmological tale is one of explosive birth, a singularity where all matter, energy, space, and time erupted from an infinitely dense, infinitely hot point. But within the EREPR framework, this story undergoes a radical transformation. The Big Bang may not be the beginning of everything, but rather the moment when everything changed form. It could be a cosmic phase transition akin to water freezing into ice, where a timeless, spaceless, and highly entangled quantum state suddenly crystallized into the expanding geometric universe we recognize. Before this moment, in this speculative view, there was no before in the classical sense because there was no time. There was no where because there was no space. There was only the quantum network in a state of maximum or near maximum entanglement, a seething ocean of pure connection and information without any geometry to give it shape. This pre-geometric state is often called the quantum gravitational foam, a realm where concepts like cause and effect here and there simply do not apply. The Big Bang, then, marks the instant when this network underwent a profound shift. For reasons still unknown, perhaps a natural fluctuation or a kind of quantum instability, the pattern of entanglement began to organize in a new way. Dense clusters of quantum links formed, and from their interconnected relationships, the first emergent property appeared, a tiny, hot, and rapidly expanding patch of spacetime. It was not an explosion into a void, but the crystallization of the void itself from something deeper. This idea elegantly sidesteps the troubling singularity of classical cosmology. There is no need for a point of infinite density because the fundamental constituents were never points in space to begin with, they were quantum links. The universe did not start from a single location, it started as a specific, coherent pattern spreading across the network. This has a stunning implication for what, if anything, preceded the Big Bang. The question itself needs reframing. Asking what came before the Big Bang assumes time existed beforehand, but if time is an emergent property of the network's configuration, then the before is a story without time. We might instead ask about the ancestor state. What was the configuration of the quantum link network like in its pre-geometric phase? Was it a static, eternal landscape of information, or was it dynamically fluctuating? Some theories suggest it could have been in a cyclic process where a previous geometric universe collapsed back into a highly entangled state, only to crystallize anew in a new Big Bang. Others propose a multiverse of possibilities where different regions of the vast quantum network crystallized into different universes with different physical laws, our cosmos being just one bubble in a froth of realities. The most profound shift is in our understanding of the universe's origin. It is no longer a story of something appearing from nothing in a blinding flash. It becomes a story of translation, of information changing its language from the raw code of quantum connection into the structured syntax of space, time, and matter. The first light of the cosmic microwave background is not the afterglow of an explosion, but the first coherent image emerging on the screen, the moment the quantum pixels finally aligned into a picture. This perspective dissolves the hardest question of all: what existed before space and time? The answer in this speculative vision is not a blank nothingness. It was an everythingness of pure potential connection, a silent, boundless network waiting to tell its first story. Our expanding universe is that story, still being written, stitch by quantum stitch, into the fabric of everything we see. The most profound experiments in physics may soon happen not in deep space, but within a chilled, shielded vault. Quantum computers, those machines built to harness the bizarre laws of the subatomic, could become our first true simulators of spacetime itself. This is not about building a miniature universe in a box, but about creating an analog, a working model that obeys the same mathematical rules as the EREPR network. Imagine programming a lattice of superconducting qubits, the artificial atoms at a quantum computer's heart. Each qubit can be tuned to represent a node in a vast, simplified web. The connections between them, the quantum gates, are engineered to mimic the proposed behavior of fundamental quantum links. Researchers could then precisely control the pattern and strength of entanglement weaving these qubits together. They could ask the most direct question possible: if we arrange the information this way, what geometry emerges? The magic would be in the measurement. By probing the collective state of this artificial quantum network, physicists would look for signatures of distance and curvature arising from pure information. Does a tightly entangled cluster of qubits behave in its measurable properties as if it occupies a distinct, cohesive region of space? If they weaken the entanglement between two groups, do the corresponding measurements suggest those groups have effectively drifted apart in an emergent geometry? This would be a breathtaking demonstration of the core principle that spatial relationships are not primary but are born from the depth of quantum connection. Such an experiment would be a bridge between abstract theory and tangible reality. It would not prove our specific universe is built this way, but it would prove the mechanical plausibility of the entire concept. It would show that the emergence of geometry from entanglement is not just a beautiful metaphor, but a physical process that can be engineered and observed. This turns quantum computers from mere number crunchers into something far more profound, telescopes pointed inward at the architecture of reality. They offer a controlled laboratory setting to explore the wild frontier of quantum gravity, allowing us to run experiments on the fabric of spacetime that the cosmos itself is too vast, too old, or too violent to perform for us. The data from these chilled, humming machines could become the first empirical whispers from the quantum network we suspect lies beneath it all. The very ground beneath our feet, the vast emptiness between stars, the stage upon which every event in the universe plays out, might be the grandest mirage of all. This is the staggering philosophical weight of the EREPR proposal. If spacetime is not fundamental, but an emergent property of a deeper quantum network, then our entire perception of a three-dimensional, local, and continuous reality is a kind of brilliant and necessary illusion. Our brains, and indeed all physical objects, have evolved within this emergent framework. We are like characters in a video game who believe the game world is the only reality, completely unaware of the computer code and electrical pulses that generate every mountain, every river, and every law of physics within it. We are not wrong to trust our senses, for they report perfectly on the rules of the game. But we may be profoundly mistaken about the nature of the hardware running the simulation. This challenges the bedrock of our intuition. We feel that space is an empty container, a passive backdrop. We believe that objects are separate, defined by the void between them. And we assume that time is a universal river flowing in one direction, carrying all events from cause to effect. The emergent spacetime paradigm suggests each of these intuitions is a useful approximation, a story that works incredibly well at our human scale, but breaks down when we ask what reality is like at its most fundamental level. There, separateness dissolves into connection. Emptiness is replaced by a plenum of information. The container itself is generated by the things we thought it contained. This is not to say our world is unreal in the sense of being a dream. The illusion is physical and consistent, governed by immutable mathematical laws. It is more like the wetness of water, a real property that only exists when a sufficient number of molecules come together in the right way. Our three-dimensional universe is real, but its reality is secondary, dependent on a more primary layer of existence we are only beginning to comprehend. This shift in perspective echoes the greatest revolutions in human thought. The Copernican revolution did not just move Earth from the center of the cosmos, it dethroned humanity from a position of cosmic privilege. We were not the focal point of creation, but inhabitants of a rocky world orbiting an ordinary star. The EREPR proposal threatens a similar demotion, but of our entire experiential reality. We are not just living in the universe, we are living in a projection of it, a holographic image generated by processes that bear no resemblance to the world we see and touch. This forces us to reconsider the very nature of causality and free will. In our emergent space-time, causes neatly precede effects because that is how the geometric story unfolds. But in the timeless, spaceless network of quantum links, the concept of before and after may have no meaning. All connections might exist in a kind of eternal now, with our perception of a linear timeline being a feature of how we, as complex patterns within the network, sequentially decode that information. Free will, then, exists within the emergent story, just as a video game character makes choices within the rules of its world. Yet those choices are ultimately expressions of the underlying code's execution. This is not a dismissal of our agency, but a recontextualization of it. Our thoughts, decisions, and actions are part of the magnificent, self-consistent output of the quantum network, playing out their destined role in the emergent geometry. It paints a picture of a universe that is deeply interconnected in ways that defy our classical understanding, where every particle is subtly linked to every other through the hidden tapestry of quantum threads, making the cosmos not a collection of isolated objects, but a single, unfolding expression of information. To accept that space itself is an illusion is to take the final step in a long journey of scientific humility, recognizing that reality is always stranger, more elegant, and more deeply woven than our senses alone could ever reveal. This vision of an emergent universe finds its most powerful language not in traditional physics, but in the science of information itself. Quantum information theory provides the grammar and syntax for understanding how the cosmic network might actually operate. It suggests we should stop thinking of the universe as a collection of things floating in space and start thinking of it as a process, a computation of unimaginable scale. The fundamental activity of reality may not be the movement of particles, but the processing of quantum information through the dynamic linking and unlinking of entanglement. In this view, the underlying quantum network is the hardware, a colossal quantum computer running the ultimate program. The program's instructions are the laws of physics, written in the language of quantum mechanics. And what is the output of this cosmic computation? It is the evolving geometry of spacetime itself, the three-dimensional display we inhabit. Every gravitational wave, every orbiting planet, every expanding galaxy is not a thing being moved by forces, but a piece of data being rendered on the screen of emergent reality. This reframes the most basic questions. What is gravity? It is not a force, but a thermodynamic effect, a consequence of the system's drive towards certain entangled states, much like heat flows from hot to cold. What is a black hole? It is not a hole, but a region of maximum information density, a processor running at the limits of its capacity, where the quantum links are so complexly woven they create an inescapable warp in the emergent display. This interdisciplinary leap brings powerful new tools to the table. One of the most promising is the concept of quantum complexity. In simple terms, this is a measure of how hard it is to build a particular quantum state from a simple starting point. Think of it as the number of logical steps required in a quantum computer's program to reach a desired outcome. Researchers like Leonard Susskind have proposed a breathtaking connection. They suggest that the growth of quantum complexity in the state describing a region of spacetime might be directly linked to the growth of that region's volume. As time passes in our universe, the quantum network is not static. It is constantly evolving, its entanglement patterns becoming more and more intricate. This increase in quantum complexity could be what we perceive as the expansion of space itself. The universe isn't just getting bigger, it is getting more computationally complex, weaving a richer and richer tapestry of connections. This leads to a revolutionary field sometimes called computational geometry. Here, geometric properties like distance, area, and volume are not taken as givens. They are calculated from the informational properties of the quantum system. The distance between 2 points becomes a question of how many quantum gates, how many operations, are needed to connect them within the network. A short distance corresponds to a simple, direct connection. A vast cosmic distance corresponds to a state where the 2 points are so weakly entangled that an immense amount of processing would be required to link them. This turns the study of gravity into a problem of quantum circuit complexity. A wormhole under this lens is not a tunnel through space, but a highly optimized quantum circuit, a shortcut in the information processing that directly links two distant parts of the network. The curvature of spacetime around a planet reflects the specific, optimized pattern of entanglement that most efficiently encodes the information of that mass. By adopting these tools from quantum computing, physicists are not just borrowing metaphors, they are constructing a new dictionary that translates the mysterious equations of gravity into the precise, logical operations of information theory. The cosmos begins to look less like a clockwork mechanism and more like a deep learning algorithm, constantly self-organizing, optimizing its connections, and generating the stable illusion of a geometric world as its output. We are inside the computation, living in the reality it renders moment by quantum moment. The quest to unify gravity with the quantum world has forged not one path but many, each leading toward a different horizon. Two of the most prominent and profound visions are string theory and the emergent spacetime philosophy behind proposals like EREPR. Their fundamental assumptions about reality could not be more different, framing a great debate at the heart of modern physics. String theory begins with a beautiful and ambitious premise. It suggests that the most basic constituents of the universe are not point-like particles, but unimaginably tiny, one-dimensional vibrating strings. These strings, dancing in a universe with many more than the three spatial dimensions we experience, are the fundamental notes. The different vibrational patterns of a string correspond to different particles: an electron, a quark, a photon. In this symphony, spacetime itself is the concert hall, a pre-existing fundamental stage upon which the strings perform. The geometry of this stage, its 10 or 11 dimensions, dictates the possible harmonies, the laws of physics. Gravity emerges naturally from the vibrations of a particular type of string, the graviton. String theory seeks a theory of everything by starting with the very fabric of space and time as a given, then building all matter and forces from the music played upon it. It is a top-down approach where the large-scale structure of reality is primary. Now turn to the emergent spacetime view championed by EREPR and its cousins like loop quantum gravity. Here, the starting point is flipped entirely. There is no fundamental stage, there is no spacetime at the beginning. Instead, there is a vast network of quantum information, of entangled links or discrete grains of geometry. Spacetime, along with all the particles and forces within it, condenses out of this deeper, non-geometric reality. It is a bottom-up approach where the large-scale universe we see is a collective phenomenon, an illusion generated by countless microscopic connections. The philosophy is not about finding the notes, but about explaining why there is a symphony at all. This creates a stark contrast in their mathematical and conceptual landscapes. String theory is elegant and mathematically rich, but it famously predicts a landscape of perhaps 10 to the 500 possible universes, each with different physical constants. Our specific cosmos is just one possibility among a near infinity. The emergent approach, while still under construction, aims for a more unique and inevitable emergence of our familiar laws from simple informational principles. It asks why our universe has three large spatial dimensions, suggesting the answer lies in which patterns of entanglement are most stable and complex. The ongoing debate is not merely technical, it is a philosophical clash about the nature of existence. Is spacetime a fundamental ingredient or a derivative phenomenon? Is the universe fundamentally geometric or fundamentally informational? For decades, these camps have often been seen as rivals competing for the same crown. Yet, in recent years, a fascinating and hopeful synthesis has begun to appear. The holographic principle, born from string theory, provides the very blueprint for how a higher-dimensional spacetime can emerge from a lower-dimensional quantum system. The DS/CFT correspondence is a precise mathematical realization of emergence, a gift from the string theory toolkit that the emergent spacetime community has eagerly adopted. Some of the most exciting work now lives in this fertile middle ground. Researchers are using the language of quantum information and complexity, ideas central to the emergent view, to ask new questions within the framework of string theory. They are investigating whether the vibrating strings themselves might be understood as excitations of an even more fundamental network of quantum bits. The old boundaries are blurring. It is possible these are not two different roads, but two different maps of the same uncharted territory, one describing the landscape from a bird's-eye view, the other from the ground up. The ultimate theory of quantum gravity may need both perspectives, weaving the vibrational elegance of strings with the connective logic of quantum links into a single, deeper story of how everything connects. Behind every great revolution in thought stand a few brilliant minds who dared to connect the dots no one else could see. The story of the EREPR proposal is woven from the insights of physicists who looked at the century-old war between gravity and quantum mechanics and saw not a wall but a hidden door. The first key figure emerged from the world of string theory, yet his discovery became the foundational map for the entire emergent spacetime movement. In 1997, Juan Maldacena, a young Argentine physicist, made a discovery so profound it sent shockwaves through the theoretical community. He found a precise mathematical equivalence, a dictionary, between a theory of gravity in a hypothetical curved universe and a quantum field theory living on its boundary. This was the anti-de Sitter/conformal field theory correspondence, a DS/CFT. While the specific universe he studied was not our own, Maldacena had provided the first rigorous example of holography in action. He proved in equations that a lower-dimensional quantum system could encode every detail of a higher-dimensional gravitational world. This was not just a suggestion, it was a mathematical proof of concept that made the entire idea of emergence mathematically respectable. It gave future researchers a precise sandbox in which to play, a place where wild ideas about quantum links and emergent geometry could be tested with concrete calculations. His work became the North Star, guiding all subsequent explorations into how space could be built from information. If Maldacena provided the map, then Leonard Susskind became one of its most passionate and eloquent explorers. A towering figure in theoretical physics, Susskind has a unique talent for visualizing the unvisualizable and explaining the inexplicable. He took the holographic principle and ran with it, championing the radical idea that our three-dimensional world is a projection. But his most famous contribution to this story is a thought experiment that feels like it's straight out of a cosmic thriller, the black hole firewall paradox. Along with colleagues, Susskind pushed the implications of quantum mechanics to their logical extreme, arguing that to preserve information, the event horizon of a black hole might not be the smooth gateway Einstein predicted, but a searing wall of energy. This paradox forced everyone to think harder. It demanded a resolution that respected both quantum theory and gravity, and it was in wrestling with this problem that the connection between entanglement and geometry became impossible to ignore. Susskind, along with physicist Juan Maldacena, later co-authored the paper that would give this entire field its memorable name, proposing the ER=EPR conjecture. He became the idea's great popularizer, using vivid analogies like quantum threads and holographic screens to translate dense mathematics into a compelling story about the nature of reality. Another pivotal voice is Mark van Romsdonk, a physicist whose work directly asks how spacetime is glued together by quantum information. In a seminal 2010 essay, he posed a deceptively simple question: what happens to geometry when you remove entanglement? Using the holographic dictionary, he performed a kind of cosmic surgery. He showed that if you take a quantum state on the boundary and carefully sever the entanglement between two parts of it, the corresponding emergent spacetime in the bulk responds dramatically. It pinches off and splits apart. It was as if he had found the geometric scissors, proving that the quantum threads of entanglement are not just correlated with spacetime, they are its literal stitches. Cut the threads and the fabric itself tears. This work moved the idea from a suggestive analogy to a concrete mechanistic proposal, providing some of the strongest evidence that entanglement doesn't just describe space, it builds it. The story also includes figures like Brian Swingle, who brought tools from quantum information theory and condensed matter physics into the fray, showing how the geometry of spacetime might share deep mathematical structures with the entangled states of complex materials. And it is fueled by a vibrant, collaborative community where string theorists, quantum information scientists, and cosmologists constantly cross-pollinate ideas. This is not the work of a lone genius in an attic, but a symphony of insights from different disciplines, all converging on a single breathtaking theme. The quiet thought experiments of Einstein and Rosen from 1935, the shocking paradox of Einstein, Podolsky, and Rosen from that same year, these were seeds planted in the scientific soil. It took decades and the minds of Maldeisner, Susskind, Van Romsdonk, and many others to nurture those seeds, to recognize that these two ideas were actually one, and to begin sketching the blueprint for a universe woven from quantum connection. They are the pioneers who looked at the deepest cracks in our understanding and saw not an end but a beginning. The universe's deepest blueprint is a tapestry of pure connection, impossible to see yet vital to imagine. Our challenge is to visualize a reality that has no space, no distance, and no familiar shapes. How do you picture a network that isn't in space but is what space is made of? We must rely on creative analogies and animated thought experiments. Picture for a moment a vast, dark cosmos, but instead of stars, you see countless infinitesimal points of light, each one a quantum bit of information. Now draw connections between them. These are not solid lines, but shimmering threads of potential, glowing filaments that pulse with a soft light. This light represents entanglement, the strength of the quantum link. Where the threads are dense and brightly lit, the connection is strong. Where they are faint or absent, the connection is weak. This ever-shifting, shimmering web is the fundamental quantum network. There is no up or down here, no grid, no geometry, just a chaotic, beautiful tangle of luminous relationships. This is the unseen foundation. Now watch as the animation pulls back. As your perspective widens, something magical happens. That frenzied network of individual glowing threads begins to blend. The discrete points of light merge, and the tangled web smooths out like countless individual pixels resolving into a single, coherent image. What emerges is the recognizable, continuous grid of spacetime itself, a three-dimensional stage with a smooth, geometric fabric. The chaotic pulse of the quantum links has translated into the serene curvature of the cosmos. This visual transformation captures the heart of emergence. The glowing network is the raw code. The smooth grid is the rendered reality. To appreciate the revolutionary leap this represents, contrast it with the classic visualization of Einstein's universe. In general relativity, we often see a two-dimensional grid representing spacetime, warped and dimpled by the presence of a massive star or planet. The grid is pre-existing, a flexible stage that gets bent. The visualization is all about geometry, a shape being deformed. The new visualization flips this script entirely. Before the star is even present, there is no grid to bend. There is only the quantum network. The mass of the star corresponds to a specific, intensely knotted pattern of glowing links within that network. When the emergence process happens, when the network smooths into a geometric reality, that dense knot automatically generates the curved region we see. The gravity, the warp, is not applied to the stage. It is baked into the code from which the stage is generated. One animation shows a bend in a pre-existing fabric. The other shows a fabric weaving itself into existence with a bend as its inherent pattern. This shift from geometry to information is the core of the conceptual revolution. We are not looking at a warped container, we are looking at the data structure that generates the illusion of a container. To make this even more concrete, think of a modern digital photograph. Zoom in all the way and you see the individual red, green, and blue pixels, a stark and chaotic mosaic. This is the quantum link network, discrete and grainy. Now zoom out, the pixels vanish and you see a smooth, continuous portrait with depth, shadow, and form. This is emergent spacetime. The image has properties like the emotion in a subject's eyes or the vastness of a landscape that do not exist in any single pixel. They are collective properties born from the relationships between all the data points. In the same way, the distance between galaxies or the flow of time does not live in any single quantum link. It lives in the pattern they create together. So the next time you see an illustration of warped space, remember there is a deeper animation playing beneath it, a silent, luminous loom weaving every curve of reality from threads of quantum information. The universe is not filled with wormholes, it is a wormhole. If the ER equals EPR conjecture holds true, then every single quantum entanglement is not a spooky correlation across space, but a literal, physical bridge in the fabric of reality. Each of these bridges is unimaginably tiny, existing at the Planck scale, far smaller than any particle we can detect. Yet their collective existence transforms our cosmic picture entirely. We are not looking at a universe where wormholes are rare anomalies hidden in the hearts of black holes. We are living inside a vast, dynamic, and constantly fluctuating quantum wormhole network. The smooth space between stars is not empty. It is the emergent result of countless trillions of these microscopic tunnels woven together into a seamless geometric whole. In this view, the entire cosmos is a single, massively interconnected structure, where every point is linked to every other point through a labyrinth of Planck-scale shortcuts. This redefines the nature of connectivity itself. Take the phenomenon of quantum teleportation, a process where the quantum state of a particle is instantaneously transferred to a distant partner. In the standard interpretation, this is a transfer of information, not matter, enabled by entanglement. But in the wormhole network picture, something more literal might be happening. The entangled particles are not sending a signal, they are already directly connected by a microscopic Einstein-Rosen bridge. The act of measurement, which forces the quantum state to resolve, could be seen as momentarily stabilizing this tiny geometric thread, allowing the information to flow through the wormhole itself. It is not teleportation across space, but a traversal through the hidden architecture of space. The information travels the long way through the emergent geometry. It takes the quantum shortcut that was always there, written into the fundamental network. This suggests a profound and beautiful unity. The weirdest feature of quantum mechanics, its defiance of locality, finds a comfortable home in the geometric language of gravity. There is no faster than light communication because there is no across. The particles are neighbors in the deeper, non-geometric web, and the wormhole is the manifestation of that neighborhood in our emergent world. The strength of their entanglement dictates the length and stability of their personal wormhole. Strongly entangled particles share a short, robust bridge. Weakly entangled ones are connected by a long, tenuous thread. This network is not static, it is a churning, dynamic sea. Particles become entangled and their wormholes form. Decoherence occurs and those threads dissolve. The entire geometry of the universe, its expansion and curvature, could be understood as the statistical behavior of this cosmic wormhole network, constantly knitting and unknitting itself. We are left with a cosmos that is fundamentally non-local, a place where everything is touching everything else through a hidden labyrinth of quantum gateways. The vast distances we see are an emergent story, a grand narrative told by a network that knows no distance at all. But if space is an illusion, what about time? Our most intimate experience of reality is the relentless one-way flow from past to future, the arrow of time that gives us memory and anticipation. Yet within the timeless, spaceless quantum network, the very concept of now may have no meaning. There is only the vast, static web of quantum links, a frozen tapestry of all possible connections. How does the river of time flow from a frozen sea? The answer may lie not in a fundamental clock, but in the way the network's information becomes increasingly scrambled and complex. Think of a perfectly ordered deck of cards sorted by suit and number. This is a state of low entropy or low disorder. Now shuffle it once, the order begins to break down. Shuffle it 1,000 times and the deck becomes a completely random, maximally disordered mess. This progression from order to disorder defines the thermodynamic arrow of time in our world, the reason ice melts in your drink and never spontaneously refreezes. In the quantum network, the equivalent of this shuffling is the constant evolution of entanglement. The quantum links are not static, they are constantly being reconfigured, with entanglement spreading and becoming more complex. This increase in quantum complexity, the growing intricacy of the informational tapestry, might be what we perceive as the passage of time. There is no universal tick of a clock in the fundamental layer. Instead, as the network state evolves from a simpler, less entangled configuration to a vastly more complex one, the emergent story it generates includes a narrative of cause and effect, of before and after. We, as complex patterns within that story, experience this narrative progression as the flow of time. This elegantly links the personal feeling of time to the cosmic increase of disorder. The reason you remember the past but not the future is because the past corresponds to a less complex, more ordered state of the universal quantum network relative to your current state. Your brain, itself a product of this emergent process, can only decode information in the direction of increasing complexity. This also offers a new perspective on the universe's origin. The Big Bang might have been a moment of incredibly low quantum complexity, a highly ordered, perhaps even minimally entangled starting point for the network. From that initial simplicity, the inevitable drive toward complex entanglement began, and with it, the emergent property we call time started to flow. The expansion of the universe and the flow of time could be two facets of the same underlying process, the cosmic network tirelessly shuffling its quantum deck into states of ever greater richness and connection. So the next time you glance at a clock, consider a deeper truth. You are not measuring a fundamental river. You are witnessing the readout of a cosmic computation, a counter that ticks forward with every new knot tied in the universe's hidden tapestry of information. The most stubborn puzzle for any emergent reality is how we get from here to there. Our world feels local, bound by strict rules of proximity. A campfire warms your hands, not a mountain across the valley, because the heat radiates outward through the air molecules immediately around it. A signal from a satellite travels at the speed of light, not instantaneously. This principle of locality, that objects are only directly influenced by their immediate surroundings, is the bedrock of classical physics and everyday experience. Yet the quantum network proposed to underpin everything is fundamentally non-local. Its essence is entanglement, a connection that defies distance, where the state of one qubit is instantly tied to another, no matter how far apart they seem in our emergent space. This creates a profound tension. How can a universe built from threads of spooky, distance-defying connection produce the rock-solid, here and there reality we navigate? This is not a minor detail, it is the central technical mountain the EREPR proposal must climb. The challenge is to show how local effective field theories, the precise mathematical descriptions of particles and forces that work perfectly in our world, can emerge from a substrate that knows no locality at all. Think of it as trying to explain the crisp, local rules of a board game, where you can only move a piece to an adjacent square, by revealing the board is actually made of a substance where every square is simultaneously connected to every other square. The game seems local, but its fundamental material is not. How does that illusion of strict adjacency get enforced? The answer may lie in a concept known as thermalization or scrambling. In the dense quantum network, entanglement is not neatly arranged. It is a chaotic, constantly churning sea. Information injected at one point does not stay there. It gets shredded and spread across the entire system at a finite speed, weaving itself into the tapestry of connections. This spreading has a limit, a kind of quantum speed limit. While a single entangled pair might seem instantly connected, to meaningfully transmit complex information across the network, to create a coherent change in the emergent geometry, requires building up a vast number of these connections, which takes time. This process of chaotic spreading can, from a distance, look exactly like local causality. Imagine shouting into a vast, dense forest. The sound waves from your voice do not instantly reach every tree. They propagate outward in a sphere, disturbing the air molecules nearest to you first, then those a little farther, and so on. To an observer who cannot see the individual air molecules, only the expanding wavefront, the process appears perfectly local with a clear speed of sound. In the quantum network, the equivalent of your shout is a quantum operation. The equivalent of the sound wave is the spread of entanglement and information through the web of links. Because this spread is chaotic and has a maximum effective speed, the influence of any event appears in the emergent geometric picture to propagate outward at a finite velocity, never exceeding the speed of light. Locality, in this view, is not a fundamental rule written into the quantum links. It is a statistical consequence, an emergent property that arises from the collective, churning behavior of countless non-local connections. It is the universe finding the most efficient way to process information, and that way, at our scale, looks like cause and effect unfolding point by point through a geometric space. The smooth, local physics we measure is the averaged, large-scale story told by the microscopic quantum chaos. The campfire warms your hands because the information about its heat has taken the most probable, scrambled path through the network to reach you, a path that our classical instruments interpret as a wave of infrared radiation moving steadily through local space. This statistical emergence of locality is a promising direction, but it remains an active frontier of research, a key hurdle that must be fully cleared for the proposal to move from a beautiful sketch to a complete theory of our specific local universe. The search for the universe's source code is now a global, interdisciplinary hunt. Laboratories and blackboards around the world are buzzing with activity, not to prove the EREPR proposal outright, but to build its machinery. Researchers are borrowing tools from seemingly unrelated fields to construct more concrete, testable models of how space could crystallize from information. One powerful set of blueprints comes from condensed matter physics in the form of tensor networks. Imagine trying to describe the complex quantum state of a vast material, like a strange magnet or a superconductor. Writing out every single interaction would be impossible. Tensor networks are a brilliant mathematical shortcut, a way of representing that immense entangled quantum state as a network of interconnected nodes, much like a circuit diagram. Each node is a small tensor, a mathematical object, and the lines connecting them represent the flow of entanglement. The structure of the network itself reveals the physical properties of the material. This tool has become a Rosetta Stone for emergent spacetime. Physicists like Brian Swingle realized that certain tensor network architectures, particularly those known as mirror networks, naturally reproduce the geometry of hyperbolic space, the kind found in holographic universes. In these models, the network isn't just describing a material, it's acting as a literal spatial lattice. The depth of the network corresponds to a radial direction inward, and the amount of quantum information shared between different parts of the network calculates the emergent distance between points. It's a working mathematical toy that shows how a pattern of data processing can generate a geometric structure. Researchers can now tweak these networks, cut connections, and watch how the simulated space responds, providing a rigorous sandbox to test the core ideas of quantum gravity. Parallel to this, computer scientists and quantum information theorists have made a startling contribution: holographic quantum error correcting codes. In a quantum computer, information is fragile, easily corrupted by noise from the environment. Error-correcting codes are ingenious schemes to protect that information by spreading it out across many physical qubits, so that even if some are damaged, the original data can be recovered. It turns out the mathematical structure of these protective codes bears a stunning resemblance to the holographic principle. In a holographic code, the quantum information is not stored in a central location, but is distributed across a boundary. A piece of information in the emergent interior is encoded in a subtle pattern of correlations across the entire boundary surface, making it resilient to local damage. This is precisely how the EREPR proposal suggests our universe works. The information that makes up a star is not at a point in space, but is smeared across a vast network of quantum links. Studying these codes helps physicists understand how the illusion of a local, three-dimensional object can be maintained by a fundamentally non-local, lower-dimensional data structure. It explains why you can't just reach into empty space and pluck out a quantum bit. The information isn't there, it's everywhere, carefully encrypted in the cosmic network. Finally, there is a push to derive geometry directly from raw data, a field touching on simplicial geometry. The goal here is to start with nothing but a list of relationships, a set of points and a measure of how connected they are, with no preconceived notion of shape or distance. Using mathematical techniques, one can ask, what is the simplest, most natural geometry that fits this web of connections? This is like being given only the flight routes between cities with no map and trying to reconstruct the globe. From the pattern of which cities have direct flights and which require many connections, you could infer their relative positions and even the curvature of the Earth. Applied to the quantum network, this approach tries to deduce the emergent spacetime geometry purely from the entanglement data between quantum bits. If the fundamental theory is a theory of quantum relationships, then the shape of space should be an output, not an input. Each of these frontiers, tensor networks, error-correcting codes, and data-driven geometry, represents a different workshop where the same grand machine is being assembled. They are not competing theories, but different sets of engineering schematics, all converging on a single revolutionary conclusion: that the universe is not a place where computation happens. It is the computation, and we are living in its magnificent, emergent display. The ultimate law of the universe might not be written in geometry, but in logic. For centuries, the dream of a final theory of everything has been a search for a single, elegant equation from which all forces and particles would spring, a master key to the cosmos. Yet this quest has often assumed that space and time are the fundamental stage upon which that equation is written. The EREPR proposal flips this script entirely. It suggests the true bedrock is not geometry but quantum information. In this radical vision, a theory of everything would not be an equation of motion in spacetime. It would be the specification of a universal quantum algorithm. The fundamental law would be the rules set for how quantum bits interact, entangle, and process information. From that single, perhaps even simple, set of informational rules, everything else would emerge as a consequence: the illusion of a three-dimensional stage, the curvature we call gravity, and even the particles that dance upon it. This is a shift from physics as a description of things moving in a container to physics as the study of a cosmic computation. What might this ultimate algorithm look like? It would likely be a principle of maximal or optimal information processing. The universe might be computing itself into existence in the most efficient way possible, constantly finding the configurations of entanglement that allow for the richest, most complex processing of data. The laws we observe, from the strength of gravity to the speed of light, would not be arbitrary constants plugged into an equation. They would be the inevitable outcomes of this computational optimization, much like the rules of chess emerge from the goal of checkmate and the movement of pieces. Gravity would be the algorithm's tendency to create dense, interconnected hubs of information. The speed of light would be the maximum processing speed, the ultimate clock rate of the cosmic computer. The three dimensions of space might be the most stable, efficient configuration for this quantum network to avoid errors and maintain coherence. This perspective offers a breathtakingly simple unifying principle. Instead of a zoo of disparate forces, we have one process: information dynamics. The long war between quantum mechanics and gravity ends because they are describing different levels of the same informational reality. Quantum mechanics is the rulebook for the individual logic gates, the qubits. Gravity is the large-scale thermodynamics, the overall behavior of the system as it complexifies. A true theory of everything, then, would be the discovery of that fundamental algorithm, the cosmic source code from which the magnificent illusion of our universe is rendered, moment by quantum moment. This journey has taken us from the silent hum of abstract quantum links to the very ground beneath our feet. We have traced a thread of thought that begins in a realm without space or time, a churning ocean of pure information where countless quantum bits are bound by threads of entanglement. From that fundamental tapestry of connection, the entire majestic theater of our universe emerges. The smooth curve of space-time, the grip of gravity, the expanse between galaxies, all of it crystallizes as a grand and stable illusion from the dynamic relationships within the quantum network. This is the breathtaking promise of the EREPR proposal, a vision that does not just add another piece to the puzzle of physics, but suggests we have been holding the puzzle upside down. By daring to propose that space-time itself is not fundamental, it offers a potential escape from the century-old war between Einstein's gravity and quantum weirdness. Here, the two are not rivals, but different languages describing the same underlying reality, one geometric, the other informational. The non-local spookiness of entanglement finds a home as the stitches in the fabric of space, and the event horizon of a black hole becomes a dense processor of quantum data. This is more than a new theory, it is a new way of seeing, a philosophical shift that redefines our place in the cosmos. We are not merely inhabitants of a geometric stage. We are patterns within a cosmic computation, complex expressions of information woven into the very fabric we perceive as reality. The distance to a star, the flow of time, the force that holds you to the Earth, all are stories told by an unimaginably vast web of quantum connection. It is a humbling and awe-inspiring thought that at the heart of everything we know there may be no thing at all, only relationship, only connection, only the silent, luminous dance of information becoming reality. What do you think? Does this vision of a universe built from quantum links resonate with you? Share your thoughts on this quantum reality in the comments below. And if you want to join us on more journeys to the edge of understanding, be sure to subscribe for more deep dives into the greatest space mysteries.